So remember we said that strong acids will have a large Ka value because remember Ka is equal to H plus times the dissociated acid over the undissociated. So it basically just means that Ka is equal to dissociated ions over non-dissociated. So the larger the Ka value, the more dissociation is seen in the acid, meaning the stronger the acid. And also the larger the Ka value, the smaller the pKa. So a base is a proton acceptor, so we're going to use a different symbol, which is Kb for the instead of Ka. So a base is going to accept a proton from water and it's going to turn into the conjugate acid BH right over here. Remember that the forward reaction will depend on the original concentration of the base, while the reverse reaction will depend on the dissociated base ions. So this is what we see right here. So you're going to get that Kb, which is really just Kf over Kr, is equal to the dissociated base concentrations over the original concentration. And if you rearrange this equation a whole bunch and then multiply by inverse log, you're eventually going to get this equation right here, which is what we're going to be using for our calculations of POH. So to solve this problem right here, to get the pH of the 0.1 molar solution of a weak acid, they give us the pKa, and we can't solve the, oh sorry, just the weak acid. Okay, so they give us the pKa, and then they also give us the concentration. So we're just going to plug in those numbers and multiply everything out and get 2.88. Okay, so for this equation, to find the pH of the 0.3 molar solution of morphine, morphine is weakly basic. They give us the Kb value, and so what we're going to do is, we can't use Kb obviously, so we're going to have to convert Kb into pKb, which is just going to be the negative log of that value right here. And once you multiply everything out, it's going to be 5.79 as the pKb. And then plugging in all those numbers, the pKb plus the 0.3 molar concentration, we're going to get POH is equal to 3.156. And then to find the pH, we're just going to subtract 14 by that number, and it's going to give us 10.844. So this slide just shows us how Kb and Ka work together to equal 14. So can an acid have a Kb? And the answer is yes, an acid can have a Kb, and a base can also have a Ka value as well. Just remember that Ka is equal to Kf over Kr, so to get the Kb value of that acid, we're just going to do the inverse of that, which is Kr over Kf. And then the same thing for bases. So benzoic and acetic acid both have Ka values. Those Ka values are referring to the unionized acid, basically the portion that's capable of donating a proton. And then for a base such as the ammonium and the methylammonium, the Ka value is referring to the conjugate acid of that base, which is capable of donating a proton. So pKa cannot tell us whether or not something is an acid or a base. It can only tell us how strong an acid or base is. However, this doesn't really apply to strong acids and bases. Strong acids will always have a very low pKa, while strong bases will have a very high pKa. But for pKa's with the intermediate values, such as these, we're going to have to look at the functional groups. So for example, something with a carboxylic acid is obviously going to be an acid. So now we're going to learn how to calculate the pH of a salt. So when a strong acid and base react, they're going to create a neutral salt, such as hydrochloric acid reacting with sodium hydroxide to create NaCl, which is a neutral salt, as we all know. And then weak acids and strong bases are going to create basic salts. So the way that works is, think of it like this. So acetic acid is going to react with the strong base, sodium hydroxide, and then it's going to make sodium acetate. And so this salt is going to dissociate completely into an acetate ion and a sodium ion. And once they react with water, water is going to react with the acetate ion and create acetic acid once again, plus a free hydroxide ion. And so basically what's going to happen is the salt resulted in an increase of the amount of hydroxide ions, which contributes to the basicity of the solution. And also, when acetic acid dissociates into the acetate ion and then a hydrogen ion, that's going to be the Ka value. But the reverse of that, when you see acetate accepting a proton, it's going to be a Kb value instead. And this is just important to note when you're calculating the pH. So remember that a salt does not have a Ka or a Kb value. It's only their parent, the conjugate acid or the base, that has a Ka or a Kb value. So to solve this one right here, acetic acid is a weak acid, and so all we have to do is plug in the Ka. We would have to find the pKa value, which is just negative log of Ka, giving us 4.75, and then just plugging in 4.75 and then the original concentration, 0.01, we're going to get the pH is equal to 3.38. So looking at this one, sodium acetate, we can tell that this is going to be a weak acid, which was acetate reacting with a strong base, sodium hydroxide. You can just tell by looking at the name or basically the formula of the drug. And so we know that we're going to need the pKb value of this because a weak acid and a strong base are going to create a basic salt solution. So we're going to take the Ka value and then we're going to convert that into pKa, which is just negative log of this number right here, giving us 4.75 again. And then we're going to get the pKb value, which is just subtracting 4.75 to 14, which gives us 9.25. And then plugging in all those numbers, we're going to get the pOH is equal to 5.125. And then to get the pH value, we just subtract 14 by 5.125, giving us 8.875. So for a weak base, procaine is a weak base, and so they give us the Kb value. And remember, to get the pKb value, we're just going to do negative log of this number, giving us 5.154. And then to find the pOH, we're going to plug in those numbers and get 3.58, and then subtracting 14 by that number, we get 10.42. Alright, so remember that procaine was weakly basic, so it's going to react with a strong acid in order to create an acidic salt. So to give us Kb, we can't use Kb, we need the pKa. So first we're going to convert Kb into pKb, which again is just negative log times this number, and then that's going to give us 5.154. And to get the pKa, we're going to subtract this number by 14, giving us 8.846. And then plugging in all those numbers, we're going to eventually multiply everything out and get 5.42. Right. So drugs can exist in their normal state, like atropine, which is a weak base. You can treat atropine with a strong acid like sulfuric acid and get a salt, or atropine sulfate right here. So in the pharmacy setting, you'll see a lot of drugs in the salt form, and the reasoning behind this is that salts are more stable, so they're going to have a longer shelf life, and they're going to be more soluble also. Also, you should be able to look at a salt and be able to tell if the drug was treated was weakly acidic or basic. So like by looking at atropine sulfate right here, we can tell that it was obviously treated by sulfuric acid, which is acidic, so this was obviously weakly basic. So the Henderson-Hasselbalch equation is so important because it lets us figure out the optimum pH, which makes a buffer solution, and this equation is going to give us the ratio of unionized and ionized forms of the drug. So let's talk about indomethacin for a second. This drug, like a lot of other drugs, exists in the ionized and unionized forms. So for indomethacin to be water soluble, some of it must be in the ionized form. But once a drug is in the GI tract, it has to be absorbed. The unionized form of indomethacin is going to be lipophilic, so therefore it's going to be more readily absorbed in the GI tract since it is uncharged. So we're just going to solve this equation here. So basically they're going to ask us what the ratio of the ionized form to the unionized form of this drug is going to be, and then the reverse of that, the ratio of the unionized form to the ionized form. So they give us the pKa and then they give us the pH, and so that's really all we need to know to find out the ratio. So A minus here is going to be the ionized form, and then HA is going to be the unionized form. So if we plug in those numbers, we're going to get 1.2 is equal to 3 plus the log of the ionized over the unionized form of this weak acid. So if you subtract both sides by 3, we're going to get that 1.8 is equal to the log of the ionized over the unionized, and then we're going to do the anti-log of both sides, and getting the anti-log of negative 1.8, we're going to get 0.016, and that is going to be the ratio of the ionized over the unionized. And then to flip it, we're just going to get the unionized over the ionized, which is just 62.5 over 1. So if you wanted to find the percent unionized, what we would do is we're going to take the part that's unionized over the total particles that are unionized and ionized. And so basically this is what we get, and it's going to be 98.4% unionized. Right, looks like that's all.